Now there are special types of vectors that every matrix has. So every square matrix, n by n. So when we say square matrix, we mean things like 2 by 2, 3 by 3, 4 by 4, where there's the same number of rows and columns. Every such matrix has a special set of vectors called eigenvectors and associated scalars called eigenvalues. So how do we know if a vector is an eigenvector? Well, if when you multiply the matrix A by this special vector V, if you only get a vector that is scaled but not rotated, that's the key here. If it doesn't get rotated but it only gets scaled, that vector is called an eigenvector. The value that it is multiplied by is called the eigenvalue, often called lambda. So from above, what we did is we said, take that vector, multiply it by the matrix A. If what you get on the output side is a scaled V without rotation, then, because we've already learned that when we scale a vector, we're basically just going to stretch it or potentially shrink it, but we won't rotate change its direction, then that would be considered an eigenvector. So an eigenvector of the matrix 2, 4, 4, 2 is 1, 1, and we want to show that it's an eigenvector and calculate its eigenvalue. So the question we have to ask ourselves is, if we take AV, do we get a scaled version of the original V? So if we multiply A times V, that's going to be the 2, 4, 4, 2 matrix times the 1, 1 vector, and that equals, again, we're going to multiply the 2, 4 column and the 4, 2 column by 1 and 1 and then add them together. So 1 times 2, 4 plus 1 times 4, 2. We add those together, we get 6, 6. Now if you look at these two vectors in two-dimensional space, 1, 1 is here and 6, 6 is out here. They both have the same rise to run ratio. And in fact, if you factored out a 6, you could see that, hey, yeah, that is just a scaled version of the original vector V. There's the original vector V. Lambda, therefore, must be equal to 6. So we basically, all we did when we multiplied A by V is we noticed that we ended up with a longer vector. So lambda equals 6 is the eigenvalue. Sounds like a fancy name, but all it is just a scalar. It's the scalar by which that vector gets multiplied when it's transformed. Okay, let's do a couple more examples. We're almost done here, and let's show that negative 1, 1 is also an eigenvector to that. So again, what we're going to do is we're going to multiply it and see if what comes out is just a scalar version of what went in. So 2, 4, 4, 2 multiplied by negative 1, 1. So the negative 1 is going to multiply the 2, 4 vector. The positive 1 is going to multiply the 4, 2 vector. And when you add those together, you're going to get negative 2, which is negative 2 plus 4. And then negative 4 plus 2 is negative 2. And at first sight, it looks like, okay, so it's still one of them is negative, one of them is positive, and the components are the same. If I factor out a negative 2 from this, then I can see that will leave me with a negative 1, 1 vector behind. So negative 2 times negative 1 is still 2. Negative 2 times positive 1 is still negative 2. And we see that what came out is a scaled version of our original vector. And so therefore I can say lambda equals negative 2 is also an eigenvalue. One of the last things that and then not every vector is going to be an eigenvector. So just to show you that I didn't pick a special matrix that just does this to every vector it multiplies. If we took this vector 2, 1, which is not really an eigenvector, but I'll just go ahead and just check this out. 2, 4, 4, 2 times the 2, 1 vector. So once again, the 2 is going to scale the 2, 4 vector. Add that to 1 times the 4, 2 vector. So 4 plus 4 is 8. And 8 plus 2 is 10. And you can see that these two vectors, they don't lie along the same line. in fact, if I wanted to make this component a 2, you might say, well, I could factor out a 4, and this component would be 2, and that's the only thing I could factor out to try to make it look like this original vector v. But then if I divide out a 4 from 10, I get 2.5, and that is clearly, this right here is not equal to the original vector. So we can also make this argument that if we were to plot these two vectors, that we would observe they do not lie along the same line. There's a rotation and a scale that took place. So 2, 1 is this vector here, but 8, 10, 3, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 8, 10 would be this vector up here. And it's kind of hard to draw to make them not look, oh, they don't look parallel. Good, okay, so you can see that this is the 8, 10 vector, and there was a rotation that took place and a scale effect. Whoops. Well, you get the idea here. And this vector here, 2, 1, so we didn't, in fact, just scale the vector. So the vector 2, 1 was scaled and rotated. And by definition, an eigenvector is one that only gets scaled. Now, it turns out that that eigenvectors are not unique, that you can find more than one eigenvector. So we earlier argued that 1, 1 was an eigenvector, but we could have tried 2, 2, or 3, 3, or 4, 4, or any vector where the x and y components are the same. And let's just show that for any non-zero real number c, that CC will be an eigenvector of the 2, 4, 4, 2 matrix. So if I multiply these together, what I should see is, okay, I'll take C times 2, 4 plus C times 4, 2. I will get 2C plus 4C is 6C, and 4C plus 2C is 6C, and already I could see that I could factor out a scalar of 6. Therefore, this is an eigenvector, this is the lambda, and it's the same as the vector that went in, just scaled by a factor of 6. So lambda equals 6 is the eigenvalue of any eigenvector v equals cc. And we can make the same argument for negative c and positive c, that would also be an eigenvector. But I just want to make you aware that there's more than one possible eigenvector. The important part is they should all maintain the same ratio. So 1 to 1, 2 to 2, 3 to 3, 4 to 4 all have a ratio of 1 to 1. And we're going to wrap this lesson up with just saying that every square n by n matrix is going to have n eigenvalues and n eigenvectors. So that means a 2 by 2, if we had a 2 by 2, we would have 2 eigenvalues and 2 eigenvectors. And we're not going to go through how you find these. It would come down to solving the equation AV equals lambda V, solving it for the lambdas and for the V's. We're just not going to get into it. It's not worthwhile, and there's some concepts there that just will turn it into a process, and it'll be hard to make sense of in a meaningful way without really digging into linear algebra. So we just need to find out how to calculate them, and we'll see how they end up applying in the next lesson. So they are values that are vectors hidden in the matrix that give us important features of that matrix. To find them, we can use Wolfram Alpha. And so in Wolfram Alpha, here's what you would enter in. You do eigenvalues, and you always check your input when it comes out, but we use these curly brackets, one to open and one to close the matrix, and then another pair for each row. So the first row this is for the row, 2, 4, that will give me the 2 and the 4. So those two values are those two values. And this 4, 2, which is now, notice a comma, another pair of brackets, 4, 2, close bracket, that will give us the second row. And then these two outer brackets, open and close our matrix. And lo and behold, here's what we get. We get lambda 1 equals 6. That's the first eigenvalue. The eigenvector that goes with that it's got a buddy, and its buddy is the vector 1, 1. For the eigenvalue lambda 2 equals negative 2, the eigenvector is negative 1, 1. And we showed this earlier, but we can see that Wolfram alpha will give us the same answer. Very nice. So again, we kind of pointed out that eigenvalues are unique and will be the same across all software. Eigenvectors are not unique, but it is the case that the ratio of y to x across any given eigenvectors is the same from one instance of an eigenvector to another. For instance, if I said that, hey, the eigenvector is 1, 2.7305, and you said, well, no, my eigenvector is 0.34372 and 0.93907. If you looked at the rise to run ratio, in both instances, it's still 2.7305. So it shouldn't be concerning if you use something other than Wolfram alpha and you don't get exactly the same vectors that I do. You can just say, oh, well, I got 5, 5. Well, 5, 5 has a 1-to-1 ratio, just like 1, 1 does. So that's it for this video. In the next lesson, we'll actually get into how we solve differential equations with this stuff. See you there.